In this lesson, we're going to add the final tools to your factoring toolkit. We're actually going to go back to lesson 5.2, where we learned about a perfect square trinomial and a difference of squares as being answers to an expansion of some specific scenarios. And today we want to be able to take those and work backwards. Let me show you what I mean. In lesson 5.2, we learned that if we take a binomial, and I'm just going to let it be represented by a term A and a term B, it could be positive, negative, whatever the case may be, and I'm going to square it. And we learned in that lesson that it is not equal to a squared plus b squared. Okay? Instead, we learned that this means, as all exponential notation does, this means that a plus b is multiplied by itself, so that there are two of them. And in lesson 5.2, we learned about the idea that each one of the terms in this binomial has to get multiplied by each one of the terms in this binomial. So we learned about a process called FOIL to make sure that that happens. And if we apply firsts times outsides times insides, which end up being AB and AB, and lasts, we get something that looks like this. Now, it's not a trinomial per se until we collect like terms. So we can say that this is equal to a squared plus b squared, a squared plus 2ab plus b squared. And this is something called a perfect square trinomial, which I'm going to refer to as a PST from now on. Okay. In 5.2, we also learned that if we take a binomial with terms a and b, and we multiply or have the product of a sum and a difference, that an interesting pattern happens here too when you FOIL it. The firsts become a squared, the outsides become negative ab, the insides become positive AB, and I know it says BA here, but I'm going to write them alphabetically so that I can see like terms a little easier. And then I end up with negative B squared. And when we go to simplify this, we notice that these like terms in the center are present in equal quantities, and therefore they cancel out, so that we're left with A squared minus B squared. And this is called a difference of squares. A difference of two things that both have a perfect square root. So today's lesson is going to focus on starting here and working backwards to the original question, or starting here and working backwards to the original question. Or in other words, instead of expanding, we are going to be factoring. So, as I said at the beginning, this lesson pairs very well with lesson 5.2 that we looked at earlier. So in order to be able to factor these, we have to be able to identify them when we are given them in a question. So what are some criteria that we can look for when we are told to factor this to help us identify a perfect square trinomial? So let's begin with an example, and I think I'll explain those identifying criteria by working through it. So here's an example of a trinomial of x squared plus 10x plus 25. And you know in your factoring toolkit that you have so far the idea of, is there a greatest common factor that I can take out first? Because this is a coefficient of 1, the answer is no in this case. We look at, are there 4 terms present? Could we factor by grouping? And the answer, of course, is no in this example. So then we recognize that this is a trinomial and we could use our little chart to help us. Okay, but before we go to the chart, I want to insert in this list in here the idea of, is this a perfect square trinomial, before we go to all this work. So here are the identifying criteria we want to look for in a perfect square trinomial. We want to look at the first term and ask ourselves, does it have a perfect square root? And the answer is yes, because its perfect square root is just x. Let's also look at the end. So this one, plus 25. Does it have a perfect square root? Well, it's positive, which is a good sign because we can't take the square root of a negative number yet. You'll learn about complex numbers in a future math course. What is the square root of 25? Well, the answer is yes, like it was here. There are two possibilities for the square root of 25. It could be 5 or it could be negative 5, right? Because negative 5 times negative 5 could give us 25, and so could 5 times 5. So far, this trinomial has met two of the criteria for a perfect square trinomial. This last criteria is a little bit trickier, but not really. Let me show you how it works. I want to ask myself if this middle term is equal to the square root of the first one, which is x, times the square root of the second one. I'll use the positive value for now, and we'll talk about when to know which one to use a little bit later, and doubled. And the reason I say doubled is because we know that this middle term comes from adding like terms from the outside and inside steps of FOIL. So it gets doubled because it's identical when we have a binomial times itself. So if I do all of that, do I get 10x? And the answer is yes, I do. So this meets the criteria for a perfect square trinomial on all three fronts. And all three fronts must be met for it to be a perfect square trinomial. And so you might say, well, why would we go to all this work to figure out if it is or not? Well, the reason we would do it is because it's going to allow us to go straight to the answer. This is going to be equal to a binomial times itself, because that's what creates a perfect square trinomial in the first place. So this is equal to x plus 5 times x plus 5. Or you could simply write it as x plus 5 quantity squared. And you would have it factored in no time. Okay? You don't have to write out these steps to verify this. You can think them in your head and maybe just put check marks as you go to see if the criteria are met. Let's leave those criteria up as we try another example. Let's try example B in your notes, which is 4x squared minus 24x plus 36. So again, when I go through my checklist of my factoring toolkit, my very first thing I apply to this is there a greatest common factor? And when you look in here, do you see anything that could be pulled out of all four terms? Well, x's can't be because this one doesn't have one, but I do notice that all of these are a multiple of 4. So let's take that 4 out first. There we go. Our next step in terms of what's left over still to factor is to say, well, are there 4 terms present? No, so we're not factoring by grouping. So then, again, instead of going straight to the table that we've been using for trinomials, can we insert this step of doing a PST check? Because if we can go straight to the answer. So I'm going to leave this here in case we can go straight to the answer. Let's check it out. So does the first term have a square root? The answer is yes. I'm going to put that over here, okay? And its square root is x. Does the last term have a square root? Plus 9. And the answer is yes. Its square root could be plus or minus 3. I'm going to write it this way for now, okay? Because we'll see which one we might want to use for the final check, which is this middle term right here. So when I look at negative 6x, is it equal to the square root of the first term times the square root of the second term and doubled? Well, it is if I use negative 3 down here. So I'm going to take the positive one out, and I'll use the negative version of that square root instead. So I do get negative 6x. So yes, this is a perfect square trinomial. So what I can then do is I can just simply write it as being x minus 3 quantity squared. And it's completely factored in that many simple steps. So recognizing PSTs saves you having to use this table. Okay, it saves you a bunch of time if you can learn to recognize them using this 3-step process. Let's look at one more example. Let's do 9x squared plus 48xy plus 64y squared. And if you're told to factor this, let's go through our checklist. Is there a greatest common factor? Well, I look at the lowest number, which is 9, because it's limiting, and I can either take out a 3 or a 9 at most out of this term. Can I take a 3 or a 9 out of these ones? The answer is a 3 for 48, but not for 64. So there is no GCF for this one. Okay. Do I have 4 terms? No. Can I insert the PST test? Yes. So let's take a look. Does this one have a perfect square root? And the answer is yes, it does. Its perfect square root is 3x. It could be negative 3x as well, but we don't need to worry about it being negative if in the factoring examples I'm going to give you in this course. Okay, the only one we have to worry about being negative is the second one because it's very dependent on the sign in the center. Okay, step number 2 of the PST test. Is this a perfect square? Yes, the square root of it is plus or minus 8y. And then we're going to look at the one in the middle. And is it the product of the square roots of both of these and doubled? So let's check. It's positive, so I'm going to choose to use the positive root of this one. 8 times 3 would be 24. Doubled would be 48. And I have an x and a y. They're a perfect match. So this is a PST. So what that means is that I can write the answer as the square root of the first term times itself and the square root of the last term times itself. And the middle will take care of itself because of the beautiful symmetry in this binomial being squared. Now, you can take this one step further, and you could say this is the same as 3x plus 8y all squared. Because again, let's reinforce that a perfect square trinomial comes from or is the result of expanding a binomial times itself. In the next video, we'll look at how to factor a difference of squares.